Okay, uh, let's begin with Dijkstra algorithm. Sorry, Bellman Ford algorithm. So here the input is your graph. This is the diacritic graph, and there is no constant on the length of the or weight of the edge. Just it should be a real number. So here we have a freedom of like having negative edges on the graph. Okay, and you are given a source node. Your goal is to find the shortest path from this source node to all other nodes. That's it. So in Dijkstra algorithm, the input was similar, but there was a constant that edge width should be a positive number, and we have seen in the last video why Dijkstra algorithm fails when there is a negative edge. Okay, and what is what was now if I so I wanted to discuss the Bellman Ford algorithm. The output of Bellman Ford algorithm is again the shortest path from source node to all other nodes, and there is one advantage of Bellman Ford algorithm. If there is a negative cycle in a graph, okay, then Bellman Ford algorithm will report that there is a negative cycle in a graph. This is the plus point of Bellman Ford algorithm. Okay. And if there is a negative cycle, we know that there is no concept of shortest path. Great. So let's see. So what I will do, I will not give the proof of Bellman Ford algorithm. So I'll give you the pseudocode and I'll give you a graph. Please go and try to do a dry run on that graph. I will explain you the pseudocode. Okay. Fine. So we are given a source node. So d of as source node will be always 0, and d of all other nodes is your infinity. So all d belongs to d minus s. Make sense? This is a pre-processing of and so here what we'll do, we'll run our outer loop for n number of times, n minus 1 number of times. So let me write down something. I will explain this to you. For I equal to 1, 2. So I will run this. So algorithm is here. I will run this thing for n minus 1 time. What I will do, I will go and check all the edges in each iteration. Okay. So for all edge, I will do something. What I will do for each edge, E equal to U comma V. I will go and check if edge UV means from then the point. So if I am saying edge UV in directed term, it means like this, U to V. Okay. So what I will do, I will go and check whether the distance of V is greater than current distance of dV is greater than du plus length of uv, and this I will do for all the edges in the each iteration of this thing. Okay, so for I equal to 1, like this is for first iteration, I will go and check this thing, and that too for all the edges. I will go and do this, check this thing. So what is this? If the distance of v is current distance of v is greater than the current distance of u plus this edge length, then I will go and this is called relaxing an edge. So how I will relax this edge? dv is nothing more. Now it will change to dv equal to du plus luv. We have seen this operation in our Dijkstra algorithm. This particular operation. This is called relaxing an edge. So edge is there, and if the current weight of this node is more than this thing, this was the greedy choice in our Dijkstra algorithm, then we will relax it. This is your Bellman Ford algorithm. For each edge, I'll go and check this condition, and if it is not in any order, you can do it in any order, and then you update it. Okay, so this process I will repeat for how many times? N minus 1 time. Okay, done. So we get the shortest path for all the nodes from the source node. Okay, what about reporting negative cycle? If there is negative cycle, then there is no shortest path. So what we do after this n minus 1 iteration, we'll do it for one more iteration. What we'll do on extra iteration, then here we'll check for each edge UV belongs to the belongs to E. So this is step you have to do after this for loop. This for loop is outside this for loop. Okay. Go and check it again. So you have done it for n minus 1 and go and check it for the nth time. If d of p is still greater than d of u plus l of u comma v, then report negative cycle. That's it. What I'm saying, initialize with the starting node as a distance 0, then do it infinity for all the nodes. By infinity I mean there is no shortest path, current shortest path for this particular nodes. Then you repeat this thing for n minus 1 time, and if there is no negative cycle, by doing this you will get the shortest path for all the nodes. Okay. And now after doing this, you repeat this process one more time. Okay. That is what nth time. This is your nth time. You repeat this process. Even if you can relax a node, like in the last iteration, then you can report negative cycle. Why it work? Why this will give you a negative cycle? Why, if it is so, then you will see the proof why it will have a negative cycle. Okay, so maybe I will skip the proof. So let me do one thing. Let me show you the time complexity. This will take constant time. This will take this will take linear time. Okay. What is the time constant of doing this thing? For each age, I have to do this thing. So this is nothing but a constant amount of work. You have to check the distances and you have to update. But you have to do this for all the edges. So this will take order m time. Great. And this you have to do for order n time. Make sense? And this again it will take order m time because you have to do it for all the edges. So overall time complexity is n into m. Order mn time complexity. Order mn time complexity. So yeah, but I'm skipping the proof. So this can be, the proof can be an extra reading for you guys. You can look at the proof of this thing. Why doing n minus 1 time is enough to find shortest path if there is no negative cycle. First, you have to prove this claim, and secondly, you have to prove this thing. If I am running one more time, and if I can relax some edge, by relaxing an edge I mean if the distance of v is x and now current distance is x and it is more than the current distance of u plus length of uv, then we have to relax that edge. So why relaxing one more time will give you, if there is a negative cycle, it will give you a negative cycle. Why is it so? So in my lecture notes it is there, and I have a graph also. You can use it as a example. So I think there might be a mistake in this graph, dry run of this graph. So go and verify this algorithm using this graph, and you can do one more thing. You create a graph where it has a negative cycle and run this algorithm, okay, n minus 1 time, nth time, and eventually you can report a negative cycle on it in that graph. So I am skipping the proof of this graph. Okay, I have a proof, so you can read it from Corbin book. Okay, so it has only, let me check how many pages are there. Yeah, 2 page proof is there for this thing. Okay, so you can read. Okay, why it works. So I am skipping the proof. Thank you. So this ends your graph. Okay, I will not teach this on Wednesday. What I will do, I will start in other topic. Okay, thank you.